No, I can do it.
Okay.
Go ahead.
Okay. So we are the University of Toronto IEEE APS student chapter. So we, you can see we have our website here at where you can go and view the events that we have upcoming. We host a seminar series as well as other types of events for graduate students and some undergraduate students as well, socials, as well as like technical talks and some workshop type stuff. We have our YouTube channel, which you can visit to see sort of past seminars, not all of them, but the ones which we're allowed to post publicly. You can view those on our YouTube channel. Yeah, we want to just kind of encourage everybody who is not already a member of the IEEE student chapter or the IEEE to go ahead and sign up. It's not very expensive, and there are a whole bunch of benefits in addition to kind of some of the stuff that I've mentioned.
Okay, thank you, Ian. So a little bit about our speaker today. Dr. Kathleen Melde is a professor of electrical and computer engineering at the University of Arizona. She is also an associate dean in the College of Engineering. She started her academic career in 1996 as an assistant professor after a 12-year career in the trade at Hughes Electronics in Southern California. She received her PhD in electrical engineering from UCLA in 1996. Her research encompasses tunable antennas and the integration of small antennas in electronics packaging. She is a fellow of the IEEE and has many positions in the IEEE Antennas and Propagation Society. So we are very excited to hear about Professor Melde's research, and thank you again for accepting to give this talk.
Thank you. Thank you, Sean. So Mr. Ian, I hope I can share.
Yes, you have the co-host.
Okay, there we go.
Yeah.
Oh, okay. So let me try to share here.
Sorry about that.
That happens, right? So I'm gonna. All right. So let me try a couple things here. I've got a double screen. Oh, good. This is going to work out just perfect. So you can see the title slide. Thank you.
Yeah.
Okay. Well, I want to say thank you for inviting me. I'm going to try to keep on time. So I don't see a time on my thing, but that's okay. Actually, I got a timer there. So, so the title of this talk is Low Profile Antennas for Chip-to-Chip Data Communications. And I added the thing called a research story. And what's really nice about these longer talks is when we go to conferences, we often just see a snapshot of different talks. But one of the things that we should be kind of sharing with each other more is how we go to make certain decisions in our research direction, because that's kind of the longer thing that we see. Now, the main part of this work that you're going to see is done by Dr. Propagation. So thank you for the invite, but I'm presenting on behalf of Prabhat and I, and a lot of this, the legwork was really done by Prabhat. So the story begins, and I'm going to show the whole slide here and then talk through this. So this work started, the whole concept of this work started about 10 years ago. It's actually started in about 2010. And it came from a call, and Dr. Treverio knows about this, is here in the States, we have a group called the Semiconductor Research Corporation, and they're a consortium of companies of TI, Intel, you know, and just a lot of Freescale, you know, a lot of companies. Oh, IBM, did I say, or say, if you don't say IBM, you're not credible. But anyway, so about in 2010, they talked about some new work that they wanted. And my work has always kind of been in this boundary between interconnects and electromagnetics. And so here's the idea is we wanted to replace the physical interconnects in multi-core computing. And so what was happening in multi-core computing is the technologies and semiconductors were advancing so quickly that we could make the cores, the computing cores, very, very small. But we kind of hit a limit, because the limit is, the technology limit comes with computing power, form factor, and then the heat and the speed. So this is where multi-core computing started coming out. So what we thought is that if we broke up the problem in multi-cores, and but we need communication between cores. Any of you all, which you guys all, that do anything with high performance computing, you're already doing parallel processing. And in parallel processing, there's two factors. There's making sure that on your processor, you are equal balance of the load of all the computing, the computing task at hand, and then the inter-processor communication. If you're waiting for communication, then your system is going to slow down. So it's a latency in it. So so this is important to the computing and the packaging industry. Again, the research has unfolded over a period that you see today of 10 years. And this really includes the work output of 4 to 5 students. No PhD students wants to be there for 10 years. So the on-ramp for this work is an advanced on-ramp. And this work really started in 2018. And I just want to give a little bit of a lesson learned, okay? And this is a fun lesson. So there were a couple times where I tried to get funding from industry consortia, and I was trying to get buy-in from some larger companies, and they said no. Okay, not that they weren't interested, I'll tell you why. But I was able to write up a very small grant, and it did not get funded, but it was a stepping stone for me to write, because I already had half the writing done, for some larger federal grants. Well, the fun thing about the company that first said no to me, now that I've got more work done, they're very, very interested in my research results. So sometimes if you hear a no, the no is not because the idea is not too good. The no could be that they're doing similar work. So I think these lesson learns are kind of important. So okay, so let's keep going. So let's look at the problem at hand. So if we look at the CPU die, we're going to be using what we call a router-based multi-chip, multi-core. And we're going to look at some models of wireless links overlaid with wired links. And we're not going to get into all that detail, but I've worked with some computer people that have looked at networking throughput, and this kind of, a heterogeneous architecture is very helpful. And so what we're looking at is solving this wireless router to router problem, because this replaces the long links in a package. So we start with, let's say this is the router that's got multiple compute cores. Here's what it would look like at the time. I think this is probably about 8 years old. There was an IBM chip. And so what we want to do is, if we had an architecture with these router chips and all these cores, and then what we want to do is have RF links for these long links, okay? So we want to have reconfigurable antennas, and we could have some diagrams here. So this was the problem we started with in 2018. Right now, the first part of the work was going to be looking at the diagonal links, and then we want to have reconfigurable antennas to, let's say, do all nearest neighbors. So let's look at scaling up here. We have a board, we have a different cores, and then we have this router layer. So more cores are possible. Now this goes back to the parallel computing. It's more suited for cases when the cores can work independently. So one of the things that came up in this work was, here's a wired interconnect where you have 2 chips, and you can imagine as the circuit gets very complicated, I call it a rat's nest. You get this rat's nest of all these different interconnects. So what we want to do is we want to look at different communication lines that we have, transmission lines. And really what happens is with the long links, you get you get bandwidth, you get delays, and then you get what we call I²R losses, and those are the long link delay losses. And so we're trying to overcome that. And here's another part of the story is when you're proposing a new technology, you always have the existing technology that you're trying to beat. And I think that's been a key part. And so kind of having to do your homework on knowing what that is. Okay, so let's look at our multi-core, multi-chip, and I'll use the term MCMC here. So again, we've got the board, we've got our cores. In this case, we're going to do a 3x3. This is going to be our standard model. Okay, idea it could be larger. And then what we did was this proposed antenna array. Now, this is a key part of this because the earlier work that we did, we had, and this is a Probot's predecessor, we had single antennas that we switched and we could have directional beams. But we decided to work with an array because there's a lot of reasons, and partly because you can get a little bit more directivity with an array. And so the other thing, when actually I call this work, I call it 3D base station on a chip sometimes. But what we want to do is we want to have our links, which are signal of interest, talking about our wireless people. And then there's obviously the signal not of interest. Now, hypothetically, if this middle core, we'll call this core E, communicating with core E, so this is your signal of interest, you want to make sure that when these two routers are talking to each other, that you don't disable communication with all the other routers. Again, you want your system, you want everybody computing, you want everybody processing, no interference and stuff like that. So the reason why you want to have the directional beams is that you don't have a lot of interference. Okay, so here's our proposed antenna array. Okay, so we have our signal of interest will be a core C and E. Maybe later we find that B and E might want to talk with each other. We can go around to the different cores. So we're going to focus on designing core E and then communicating to all its nearest neighbors. Okay, so here's our proposed architecture. Now, there's a lot of reasons why this proposed architecture was included. So it's an antenna array that is above the chip. And then we also have this very low loss substrate. The reason why we'll do this is we want to have this hybrid. And so it's hybrid, the surface wave structure, so that we're using the free space antenna communication, but we want to use a relatively not so high epsilon R and low loss antenna substrate, because that will help guide the way. That was the solution that we chose at this time. We'll evolve to a different solution later in the research, and you'll see that. Okay, so here's the communication. So long links are avoided. Okay, this is near the speed of light communication. So if we have the antenna beams, that's going to impact, again, the near speed of light also is going to impact the antenna substrate. Low wiring complexity. I gotta get some water here. The nice thing about getting rid of wiring too is you can reroute your lines. If you have fixed lines and wiring and something breaks, then you don't have any way to reroute your signals. And so that's what's really nice about this router to router. And then again, the much lower I²R losses, and these are losses due to if you had wired. Okay, so let's look at, again, we're going to compare wired versus wireless. We can do this pretty quickly. Here's the old wired. Here's kind of the issues. Okay, if we have just wireless, okay, but we're changed at the end of the lecture. We've changed a little bit of direction. Okay, you have the antenna array, but we've also found with this hybrid space conductor, and again, this was the solution in 2018, is that we can kind of contain, one question was, let's say if this guy was communicating, could there actually be coupling down into the chip that could cause some interference? So we thought that this proposed hybrid space and surface wave could help channelize that, that communication. Okay. let me go to the next one here. Okay, so let's talk about the antenna and the link metric. I think I can do these pretty quickly. Let me just bring the whole slide up here and I'll talk about these things together. Okay, so this is actually very important, and this is really something that kind of switches how antenna designers think versus how interconnect people think. So antenna designers often will look at the gain bandwidth, okay? And we're going to be looking at this work. I didn't say at the beginning, but we're going to be looking at this work specifically at 60 gigahertz. And there's a reason why the 60 gigahertz bandwidth is good. Number one, if you have a computer, okay, or a device, then that 60 gigahertz communication is going to be contained within that box, because there's something beautiful that happens at 60 gigahertz, that there's what they call attenuation windows. So generally, if you're outside the box, there's a large attenuation window, and it's usually due to water and the atmospheric effects, so that if you have two boxes that have this 3D base station on a chip, they're not going to be interfering with each other so much. So that's a good thing. Another thing about 60 gigahertz that we all know is that there's a really great MIMO and wireless band out there. And so what's really nice is, as we think about having the receiver, the transceiver to build this up, there's, and I hope everyone knows about the term COTS. I think I would expect Dr. Hum to have told you that in your classes, and that means commercial off the shelf. So that means when I'm developing a new technology and I have the whole transceiver that I need, if I've got low cost commercial off the shelf transceivers available, then it's going to be a more adaptable technology. So we talked about the antenna part here. I talked about 60 gigahertz, but when we look at link interconnects, we also like to look at the integration of the S21. Okay, so oops, I went back one here. Maybe if I can go back one here. Okay, so we actually like to look at this link interconnect, and this is the one that we're going to be using. So we're looking at the S21 link interconnect and that bandwidth. So again, it's a little bit departure of what we know from antenna people. And the S21 is actually kind of good in this case, different from just looking at gain. Actually, Prabhat's got it all here, but we also look at the directivity of the antennas, and then also the matching to their transmit and receive circuit. So I think it's a little bit more comprehensive approach than just looking at gain. So that's the metric that we'll be using throughout this work. Okay, so all right, so the antenna design. So this sets some requirements on the antenna design. I'm going to walk you through what we did with the antenna design. So we have switchable beams, high directivity and radiation efficiency, large bandwidth, small footprint that can be amenable to chipset antenna size, and then seamless connectivity with CMOS chips, because we need to integrate this. The other thing that's very interesting, that's very different from cell phones, is that the antennas are switching in that horizontal plane. Okay, very different from a lot of reconfigurable antennas we might see for radar. Okay, so this brings up this next work. I want to move on a little faster. Okay, is we did a comparison. If you look at the literature, when you look at switch beam arrays, you see a lot of them for linear arrays. Okay, which came from radar, might come from cellular base stations. But really what we're trying to do in this 3D base station in this horizontal plane is do this scanning in the XY plane. Actually, I like to point these things out for students because it's something that I do just naturally. I'm a big stickler for coordinates. Okay, when we start looking at the overlay of the antenna patterns and stuff like that, we always want to normalize you guys to the coordinates. So I'm a very standard spherical coordinate person in the XY plane here. Theta's, this is the theta equal 90 plane. So this is how we're going to do our antennas in this case. Okay, so that's the case. So we're going to do this planar array of 4 elements, and we felt that we could put 4 elements on the chip. Okay, and so what we're seeing in this slide is Prabhat is starting to work on how he's going to package this, because we want to fit into a standard CMOS chip. So we started looking at how we can get those phasing positions to scan. And so this is just array calculations with before the element factor, just an array. And so we found that with these different phase factors here, okay, that we can get those diagonals with this collection of different phasings, okay. And in this case, the spacing between elements was 0.35 of a lambda. Okay, and so we're starting to see different cases here where we can switch it around. Okay, so now within the array, the next step, and I really like to see how this unfolds here. I'm going to show the whole chart here, so again that I can bring this out here. So so we have the array orientation, and next we have the element factor, and this is always a huge choice. Okay. In addition to my giving this talk today, I'm actually reviewing some proposals for federal funding, and it's interesting to see how some people are kind of have a gap in their discussion, because you need to make sure that your element factor, in this case a center fed circular patch array, is matching or in alignment to what kind of array problem. So Prabhat found this beautiful center-fed circular patch array with side vias. He did not invent this, but he found this work. I do think that being a great PhD student requires being I call him being a digger. So you need to be a little bit of a forensic scientist, and that means looking at really going out there and searching what other research is out there. So this is a this antenna was I think it was communicated by Dr. David Jackson from University of Houston, who's a very solid researcher. So it's this patch antenna with these side vias, these 4 side vias. And it is actually these side vias that work to create the surface wave that really creates this sidewards radiation. So Prabhat did some modeling here. He looked at, here's the antenna. Again, we have, because he did such a good job at putting the axes on here that we know where theta is going to be coming down here, and he can scan that out. And so here's the configuration. I call this the stack up. This is a low loss, low epsilon R material relatively. Oh, it's right here, 3.55. Okay, low loss tangent. One of the things that Prabhat was playing around in this work, and this makes a lot of sense, is that he's playing around with these cases with the ground plane sizes. Now, this is not a recessed ground plane. He just has the pattern plot over the square ground plane. So it's no recessed patch. But what do you expect? Okay, and does this follow our intuition? So in one case, he's looking at the patterns. If you've got a 7.3 by 7.3 millimeters squared ground plane, and in this case, he's got a larger ground plane. And as you'd expect, if you have a larger ground plane, you might expect more directional antennas. And that's exactly what you have here. So you've got this kind of omnidirectional, and then you've got these more themes here. So, but he was starting to play around with to see what kind of ground planes could this work on. He's going to be choosing the smaller ground plane to fit this on the package, and then to get the directionality, that's when we're going to use the beamforming. Okay, so and we all know that from arrays. So this is the element factor that would lead to the arrays. Now, Parnaz, I hope you're checking the chat. One of the things I do on Zoom is I like to chat a lot. So at the end, we can use that for discussion. Okay, so when you have an element, what's the first thing you do? You design the element for the pattern, but then you also need to match it. Okay, so Prabhat he actually developed, I don't have this presented here because I want to get into bigger work, but he created a cavity model and an analysis model. He did a beautiful job, and again, it was based on the prior work that Dr. Jackson and his team created, and then he simulated this on one of the most popular simulation programs out there, which is HFSS. And you guys, as all grad students, you guys can come up with your opinion on do you think that analysis and simulation match each other? For the most part, I think he did a pretty good job, and he has it matched right around 60 gigahertz. These are all the losses. I'm a big proponent of looking at the impedance charts. And as you expect, here's the resonance. I always try to match at the tail of this resonance. So we're looking for 50 right here, and then 0, 0 down here. If you can flatten those two curves, usually it's the reactance curve that's the harder one. If you can flatten that curve, that's where, oh, flatten the curve. Sean, we got flatten the curve here, man. That's our new term here. So if we can flatten that curve, then you can usually get wider bandwidth. So I hope this follows some of the principles that you agree with. Okay, so then element, now we go into the realization of the array. Okay, so these are not touching, even though they look like they're touching. Okay, but when you start modeling the array, obviously you're going to have a little bit of mutual coupling. So Prabhat did a very good amount of work with modeling the array, okay, with our basic element that's matched, okay, and started looking at the beams. He started putting in the phase factors here. Let's go. Can you guys, you guys cannot, if I have to start pointing over here, I'm pointing on the other screen. Okay, I'm getting better here. Okay, so, all right, let's do, oops, okay, good. So here's our circular patch array. He's looking at all the different cases here. Okay, this is what Prabhat did here was what we often do. You're not seeing all the results, but we often do, we'll do a parameter study to see how good you can get the matching. I'll go over here. You guys aren't going to see my face though. So he started looking at the different parameters. He started looking at the distances, the diameter, the B. The B was the spacing. No, the B was something with the vias. Anyway, so yeah, sensitive via the via diameter. So you can kind of see he's trying to optimize that. Okay, so we've got an array here. All right. So the question is, the next question of this research story is, how are we going to implement this phase scanning? Now we're in this on-chip, on-package environment. If you have something that needs a phase shifter, that's an electronic phase shifter, it's going to be bulky. And then if it requires power, we're not going to like it too much as users because it's going to drain our battery. Okay, so we want to be a little thoughtful in terms of how we implement something. We really like this work because it was pretty much simple phase shifting. Okay. It was actually a conversation at a conference that I had with someone about this problem that led to this solution. So someone said, why don't you try this? So that, again, this is a research story. So this is what's great about sharing the research with people. And so we decided to look at this Butler matrix. It's a very famous type of circuit, but we also were implementing it in a 2D manner. So there's some packaging work with that. So let's look at the Butler matrix. I'll bring, again, I'll bring the whole slide up here. This is a lot of fun, okay. Prabhat loves these animations and I love them too. Okay, but let me bring them all up here. Oh, okay, I went back one too far. Okay, there we go. So here's the Butler matrix and the packaging. So let me just kind of give you the bird's eye view. So we have, this is the array. Okay, it looks big, but Prabhat was able to package this. Okay, so a Butler matrix is probably been out for 50 years. It's a very classical antenna switching, been used for linear arrays for a very long time if you have 4-element array, but it hasn't been implemented in packaging. So you have 4 ports that feed your array, 1, 2, 3, 4. So if you feed port 1, it'll just enter all the energy into port 1. You create one beam direction. Okay, if you want to change the other diagonal beam direction, oh, he did a very nice job here with making the table here of the phase shifts that are built into the Butler matrix. He also gave a diagram on where that would be with the feed point, and then he also gave a third diagram of where that would be for the beam position. So this is very complete that you can kind of follow the path. Similar with port 2, port 3, and port 4. So the way that we would actually invoke the Butler matrix is with a very simple switch network that we did not include in this research. Okay, so that's kind of what's happening here. And these 90-degree hybrids are, again, part of the recipe of the Butler matrix. Okay, so this is where I would say he spent quite a bit of his time on this. Okay, he actually went with a little bit larger case here, but let me bring up all these slides again here, and then I'll unfold the slide. Okay, one more. Okay. Okay, so he spent quite a bit of time figuring out how to lay this out in a package. And so he made some key choices, and this is part of the research story. Okay. As you know, it's funny when you see research that people are doing, because you're seeing the end of the story. What you don't see is all the hours and all the trade-offs to make these solutions. And you guys know that from your own work. So one of the things that Prabhat did is he chose to use 100 ohm lines to make thinner lines to reduce the coupling. Okay. Now, what do we see here at the antennas? Okay. We designed the antennas. He didn't go back and design the antennas, but we designed the antennas for 50 ohm impedance. So although he did this for 100 ohm lines, right before he gets to the antennas, he's got to fan out to 50 ohm lines. And he does that with a multi-section transformer so that he can get the bandwidth. Okay. If we really wanted to make this a little bit more compact, this is an area of opportunity to try to make it more compact. As you guys know, when you're feeding the antenna at 50 ohms, you don't have to do that. You could design it to all be a 100 ohm system, but anyway, he just didn't go back and do that. Partly because his advisor was putting a lot of pressure on him to get things done, so he just decided to keep on it. So this is the routing that he did. And we looked at the scattering parameters. Okay, so we have all the different, the port division, okay, that you'd expect. If it's a two-way power divider, you expect -3 dB at each port, right? If it's a four-way power divider, in this case, you've got the -6 dB is what your nominal is going to be. Okay, so that's normal. And then here's the phase shifts for the different cases. There's one more slide. Okay, there we go. So he's showing some of the different the phase variations. Now, one thing that we should do, okay, if we wanted to, was actually to implement a switch network with the phase shifters, and then you would compare the size and the loss and all that stuff. But we chose not to do that. And again, a lot of that it didn't just come magically. I did say it was helped by one conversation, but it was also, you know, looking at the research and looking at the loss and the implementation of circuits. So you guys know this, when you're sitting with your advisor, you're sitting with your research team, you know, you make choices and you want to continue that choice, test it, and then compare it. You don't want to keep second guessing it all the way. So anyway, so there's some good things here. All right, let's go to the next slide here. Okay. Okay. We'll talk about this coplanar waveguide to microstrip in a minute, because this is an interesting part too. And this is okay. So love it. Okay, this Prabhat created an animation about if he puts the energy into port 1 and how it's divided up with the power divider into the array, which is here. So I thought that was very nice. And again, here's at 60 gigahertz. So power split equally into the hybrid. Okay, now when we do measurements at 60 gigahertz, and this is something that has been very important to me for packaging. Okay, so one of the things that we try to do in our research group a lot is I kind of invented this description. I didn't, but I call it the research triangle. Okay, so when you have, I believe, when you have research and you're defending a new technology, that you want to use all three sides of the research triangle. On this research triangle, we have analysis at the top, simulation on one of the sides, and then measurement on the third side. And so I try to convince people that if you're trying to convince your advisor or convince people that maybe aren't so convinced that you've got good research, is you want to take your, often if you can equate analysis and simulation, then that's convincing. Okay, you've got two independent things, and yes, you might be right. But if you can do analysis, simulation, and measurement and get them to all to agree, you're right. Okay, you can have people, I always call it shoot bullets, but it's a nice thing. You know, you can always have people question your work, but if you can perform research and look at it from all three edges of that, or all three vertices of that triangle, you're right. Okay, so anyway, so in measurements at 60 gigahertz measurements are are difficult to make, but we've perfected this in our group on packaging. And so we like to use on-wafer probing. I believe that coax-based measurements at 60 gigahertz are difficult to make. So one of the things that we use are coplanar waveguide-based measurements, and we use a multi-line TRL calibration method because the repeatability, I think, is superior at this frequency than SOLT, which is short open load through measurements at 60 gigahertz. That might be changing over time, but I trust these the most. So to be able to make his measurements on his, Prabhat constructed a conductor back coplanar waveguide to microstrip transition. So in practice, he's going to have this Butler matrix all based on a 100 ohm system. Okay, and so you could put all the electronics that all is going to be behind it. And I am way behind because I'm only on slide 18. So anyway, he created this transition. It's going to be a 50 ohm transition because most microwave network analyzers are based on 50 ohms. We do the so he had to build this in there. Okay, so let me go quick here. Okay. And so he got pretty good results on this. Okay, he designs the transitions on HFSS, learns the fields, and then created this very nice multi-layer antenna module. Again, these are, why is this big? This is big because of the coplanar waveguide, and this is only for the testing artifacts. Okay, so let's go through this pretty quick here. Okay, so we have all of this. And then we show the stack ups here. So he was able to compare, okay, so he was able to compare the standalone antenna and the module. Okay, and we got very nice bandwidth. So things aren't changing here, but these are some of the I'm going to show the animation real quick because it's nice. So he's trying to show the stack up of how he would do the module here. Prabhat, did you do this on SolidWorks or HFSS?
Yeah, this is done on SolidWorks. So
Okay.
HFSS was where the modeling was done, and then
Thank you.
I exported to SolidWorks. Yeah.
Yeah. So okay. So yeah. So you can see how that goes very nice here. Let's talk about the field visualization. Prabhat also wanted to understand the fields because we have this hybrid. So we have the radiation. We've got the TM0 surface waves, which is from that patch antenna. Okay. Talks about the I don't want to call it 1/r squared, but talks about the losses in that that you have. Okay, we've got the theory and the simulation. He modeled a lot of this chip stuff on HFSS. We got a nice video here. He's going to show you. We got another video here too. Okay, there we go. So we're looking at the waves here. He's got the ground plane here. He's got the antenna up here, and then we're looking at the waves. Now he's going to look at, we're going to look at a link budget here in a few minutes here. Okay. What do we have here? He's looking at the effects of the feed layer. He wanted to look at, oh, so he looks at the module and the gain. So here, what this is telling us is that there, oh, let me keep going. That we have a lot of point-to-point communication because of the extra dielectric layer. So this is good. So we looked at the efficiency. Now, obviously, if you have an extra dielectric layer, the efficiency is going to go down a little bit, and you'd expect that. But that's what we're really going to be looking at is the signal to noise ratio and the communication in kind of the 3D system. So these are kind of intermediate metrics, but we also want to be looking at what happens in the system. So we have the standalone and we have the modules. The modules definitely a little bit more directive, and we can kind of control those so that you have the single antenna communication. Okay. So now he's going to be looking at it in the modules. So this is kind of more of a, this is the link budget on a chip. So as we talked about before, we're going to be looking at we're only looking at the diagonals. Now pretend, because we did have the 3x3, but since this work is only looking at the communication of the diagonals, he just went with a prototype with just looking at the diagonals. So we're going to call the E is going to be the transmitter and C is going to be our receiver. Actually, I think it's, yeah. So those are the signal of interest. And then the other ones are going to be the signal not of interest. So he's going to show how this is put together. And he's going to be setting up a structure for these different cases. So Prabhat actually created, we'll have a picture of it, a 5x5. So earlier he just looked at the single module. Oh, and I love it because he calls this MAM. So it's a multi-antenna module. So we're going from MCMC to this multi-antenna module. And so he's actually now scaling up his work and looking at that larger communication. Again, we have some areas that if we wanted for improvement, we could get rid of these and we could get rid of those to make it smaller. But we've got the 2x2 patch array, and then we've got the switchable beams. Okay. Okay, so how are we trying to look at this? And I want to applaud Prabhat for this work, and this is what we see in a larger context. That's why I call it a research story, is that, and you guys know this in your own work, every time you present your work, other people that are not so close to your work are going to be asking you questions. And then you get a little bit better at perfecting your work. So talking about mapping coupling, side lobes, back lobes. And the other thing is talking to larger communities like packaging communities or communication communities. You start broadening your scope of your work, and it also helps you understand what you're doing better. So I know these charts look very good, but he spent a lot of time perfecting this. Okay, so he's got the communicating pair, which is EC, and then everybody else is called an interfering pair, which is fine. Okay, so lots of work on the setup and calibration. Okay, Perez, you can take the survey, but don't you guys think this is pretty? These sure look pretty, right? Copper looks pretty. As you guys know, we always put a size reference. So in this case, the US penny is a size reference. I'm real picky about when people use coins to make sure, Sean's gonna love this one, but I always make sure that you look at the year of the coin to make sure, because then you get a time date, okay? So this is a nice little circuit, right? It's not very, yeah, good, yeah. It's not much larger than a penny, and he's got the 5x5. So anyway, I think it's very beautiful. It's got that multi-layer stack up with all the vias. So anyway, now one thing that Prabhat has in here, I'm not going to spend a lot of time on it, but what do you think is happening on this part of the circuit? I know it's not a class, it's a lecture, but there's a little bending in these circuits, okay, because of the size and because of the processing. In the future, that would have to be taken into account. Prabhat in his work did include the bowing effect, but I'm not going to show it here because I want to go into the next evolution. So we've got C and E here, the communication pairs. We've got the beautiful lab set up. Prabhat did a beautiful job at, sorry, Prabhat, I can commend you, I can't commend myself, but he also had to restructure our probe station so he could get in the probing at these different angles. That this was quite the work here. Okay. If you're not familiar with the multi-line TRL, we have these nice little structures. We use conductor back CPW, so we put the ground plane underneath here. Okay. All right. Oops. And then you can see him, you can see where he was probing this. And then again, you can see on this picture how it wasn't very flat. But that's, he's got some work on that he's presenting in some publications, but we're not going to talk about this. Nice close up of the CPW probes. Okay, so he's looking at the reflection coefficient of the case E. He's looking at the signal. This is CE, 30 dB there. And then he's looking at the interference. So what we're hoping in this situation here, I'm going to get a few more slides here, that, okay, I'm going to get all the words on here. Oops, I'm looking at the, okay, there we go. We're hoping here that you hope that the interference is lower than the signal. So we've got about a 10 dB. I mean, we can all look at this. These are all about 40 dB down. We've got this close to 30 dB. So he's got a definitely lower interference here, which is what we wanted. Blue is simulated, the dotted is measured. The variations, now a couple things about the variations here, obviously, is when you start, and you guys should know this, I hope you guys know this, but when you start getting in the lower dB levels here, measurement and simulation accuracy can be difficult. Prabhat did a decomposition on the bowing effect on this, but again, I'm not going to be presenting this here because I want to get into his evolution work and I'm running out of time. So without a lot of detail here, he actually broke down the work in the different kind of waves that are happening here to get a deeper understanding. And we have a field animation here. So we have chip 1 here. This could be chip E, I guess, and this could be chip C. There we go. And we're starting to see how that is breaking down. Okay. I'm going to go through this very quickly. Prabhat did some link budget calculations. I have 42 slides here, so this is so yeah, we can do the other ones pretty quickly. So Prabhat did a very nice diagram of how he's doing. Let's say this is, again, let's say this is array C. It's right here. This would be array E. So he wanted to again come up with the whole link budget on how that's looking at to look at the SNIR calculations. Here's his assumptions. And on the next slide, we see, oh, this is beautiful work. So we see the SNR, what is, oh, there's a poll. How impressive is, oh, good job, girl. So thank you. Yeah, come on, looking at stuff is kind of nice. Thank you guys. Okay. So we have the SNR measured and simulated. Here's a little bit of difference here. Okay, I love it. I love the honesty. I love it. So, okay. The other thing that Prabhat did is he started looking at the different communication schemes. And in this assumption, if he assumes the 64-bit QAM, you've got the bit rate that brings your signal to noise ratio, and you can start looking at your compacting out your data rate. This is not my area of expertise, but this is more in the communication domain to really communicate it into a gigabits per second. Okay, I love the poll. Thank you guys. Great. Good. Okay, good. Thank you. Okay, so let's look at the comparison of other works. So at the time, and we can, here's the other work. We like to reference our publications here. I'll be in 2018, this was where the work was. So Prabhat looked at this work, looked at the number of beams, looked at the form factor. So at the time, this was one of the smallest chip-to-chip on-packaged antennas that are out there. So Anyway, so that's kind of his discussion here. So let me just go to our next where we evolve the work. So I think Prabhat squeezed a lot of dB out of that circuit project, okay, and really brought it from initial concept up to communications. So remember, we said that we wanted to eventually bring it to a work. So I'm going to get rid of the poll if we can. Thank you. Sorry. So I know that was sitting there. So we wanted to think about what could we have to have 9 possible beam scans. And at first we were looking at how we could take that patch array and make more elements and do some more things. But then Prabhat had some other ideas, okay? So, so we changed the problem so that we could talk to all different people here, okay? And really thought that adding more elements to that beam or more phase shifters was a little bit, we didn't really want to go that direction. So Prabhat decided to actually, now another antenna that we know that's different from an array that's a directional antenna are horn antennas. Okay, so horn antennas are, that's one thing we do as antenna designers is we look at our toolbox, okay, and your professors help you understand what's what the basics of that toolbox is. So what's in another antenna in that toolbox? But then our job is how do we manufacture those antennas in the new constraints, and in this case, a packaging constraint. So I've only got a few more charts here. So what Prabhat went through, okay, so he changed his thinking to try to do this this integrated switch beam and horn antenna. So we've got 8 horns here that it's all going to be based, and so this is a surface wave horn, a printed horn that has these corrugations in here to a surface integrated waveguide. And then this one we would use a switch. So what we see shown up here, okay, is that up inside, before we go with this surface integrated waveguide, we've got vias here to separate them, but we've got this coplanar waveguide fed transition to the surface integrated waveguide. Okay, so Prabhat spent a lot of time figuring out what the corrugations are going to be, and then what the taper is. It's for matching directionality, all those type of things. I think he took some guidance from previous work, but he also did some optimization on HFSS. So let's keep going here, okay? Because this one he's starting. Right now, Prabhat's in the process of fabricating the MAM for this, okay, the multi module. So you can see that he's got the single antenna here, okay, no phase shifters needed, okay. A little bit more gain, I believe he had with the other antenna, okay. Gain can be increased by increasing the length of the horn, but that results in larger antenna size. And we already know that, right? The larger the aperture. Okay, so we've got a few more here. Okay, so he did some analysis on this, but he also did more simulation. And so he set up a very nice structure here. They're always upside down. You can see the coplanar waveguide here. And then he wants to do some transmission lines, okay? One other thing, these are details, but when you have a probe station, you generally have a metal chuck here, okay? So we had to save some foam from some of our packaging to be so that it simulating an air environment. I know those are obvious, but sometimes it's nice to point out the obvious. So he looked at the separation here. Let's keep going. Okay, and remember our metric is S21 here. So he's looking at line of sight. And then Prabhat, this is where he actually did some things with the probe station. Again, look at how, so you can see that these are like little icebergs here, right? He had to build up these little styrofoams, but he had to really line these up and then adjust the probe station. I think we're going to have the results here of the modeling and the simulation. Okay. And I'll tell you one thing. So you see the measured and simulation on these S parameters. I think he's getting better agreement with this than he was with the previous antenna. Okay, so we're starting to see what these look like. These have to be the S11s up here. These have to be the, let me see what he's got here. So he's got good agreement. Sorry, are these labeled here? Oh, they are labeled here. So yeah, these are the S11s up here, the measured and simulation, and then these are the links here. And what do you want to have here again? You want to have, this is your line of sight, also called the signal of interest, and then this is your not of interest. So he's got that there. Okay. And this is where the work's going to end here. He's looking at again that division. Prabhat, I do think that the order that you just sent me today with the fabrication has to be multiple ones of these so you can do the MAM measurements. Is that correct, sir?
So we actually already have done the MAM fabrication, and then we done the measurements. So this next work is we're actually integrating the switches with the antennas, and then so
okay.
It's a more complete system. So
Thank
you can
you.
have yep. Yeah.
Okay, thank you. Thanks for telling me that. Okay, that's really good. Actually, Prabhat's going to be transitioning off this work because it's over with, and he's going to be taking on some new work here. So, or a new venture. So this is going to kind of wrap up kind of the work that he's done in this evolution. And as you guys know, as PhD students, our work is never done, right? So it's always started by others, but it's never done. I'm sure as you guys are listening to this, there's some questions to ask. Here's some previous work that Prabhat has done. You can Google him or Google me, and you can see some of that evolution. And then before I take questions, if you guys have not seen this, I know George and Piero and Sean have seen this, but this is my shtick, if you want to call it that. So how many of you guys have seen this advice from Antenna? Paranaz, have you seen it? No, good. Okay. Piero,
Nice.
have you seen it?
Yes, I saw it.
Okay. Yeah. So this was in the AP magazine. So I wrote this out for a conference one day. And I guess as I move on from research to administration, this is my last contribution. But so I always say, you know, what would the antenna do if it was giving us advice? And so it's look radiant, keep a low profile, be a ray of light, resonate with others, stay focused. And my favorite is there's nothing better than a perfect match. So I think that's the advice the antenna would give us. Yeah, Piero, you can, oh yeah, you said you've seen it before. So, okay. So that's where we are. And I'll be willing to take questions or comments.
Nice. Thank you very much. I should congratulate Prabhat for this amazing work. I can appreciate how much work has been done to get just the fabrication and simulation match, let alone doing such a amazing job in designing it.
Yeah, thank you.
Nice. And thank you, Dr. Melde, for explaining this such a interesting way. I'm sure everyone was so engaged in this talk. Okay, we do have a question from the chat. Any reason for not choosing an active phase shifter, transistor-based, bandwidth versus size? I guess the question is what is the trade-off? Yeah.
Yeah, so that's an absolutely great question. At the time, because you know everything is kind of time dated where you are, we really wanted to avoid anything that would require a power that would require extra power and bias, partly for the complexity and then partly for the battery. But that is something that could be looked at, because I think as you build out the more complex system, you know, getting into the intricacies of how you wire it, what the DC power required for all that, it goes much deeper than what you're seeing here.
Yeah, just to add on to that, I think there is also a lot of power loss. At 60 gigahertz, these phase shifters have a lot of very lossy at that high frequency, so that we decided to go with the transmission lines and passive structures for most part.
There is a follow-up question that
Yes.
can that be taken from the chip itself using VS?
Good question. That's a very good question. I don't have an answer for that, but why not? Yeah.
Nice.
Oh, what was the so it's actually taken from the chip itself, huh? Right. What is taken?
What he's trying, could you do a remote biasing with the phase shifter,
As in, like, you can have the phase shifters in the chip itself and then take the phase shift from the vias to the board where
I mean,
we have the antenna.
So we absolutely haven't thought about that, but maybe.
Yeah, I think you would need a so you're talking about baseband, right? Is that before it's actually converted from like to the analog domain?
Yeah, sure. Like you have a chip. The chip has transistors and all. So if you are planning to have an antenna on the substrate itself above the chip, so you can have this phase shifter circuitry within the chip itself, because it will be very small.
Yeah, you can do that, integrated with on the antenna substrate itself, right? And then and this could be done in the digital domain as well.
Yes, that's
then
right.
but analog domain, I think would be the way to go, I think, because you would need a very high digital to analog converters, and that could be, that means more power loss, and so I think that's why we decided to go with the simplest of the ideas. So but great questions. Yeah, I think it's something something we can look at going forward.
Sure, thanks.
Mm-hmm.
Yeah, there is another question from a very
I can see the question. So Bassam wrote it, right?
Yeah.
Yes, sir. So it says, I'm surprised about the agreement between the simulation and the measurement results. Did you resimulate the model? So Bassam, this is a very important question, and the solution that you're talking about is really important. So when simulation and measurement don't match, it always creates an interesting pivot point in the research, an interesting kind of point of controversy. Okay, it's a learning point. Sometimes it's the dielectric materials, but one of the things that's in our power as researchers, which is great, is we can always, we can't remeasure and refabricate and all that stuff, because that really takes a long time, and a lot of times the contracts are limited with budget and all that stuff. But we definitely could go back and simulate, because I always try to simulate the problem, simulate the errors, and it's kind of fun. So Prabhat actually took quite an effort to change his HFSS model to simulate the bowing. Okay, he tried to understand why the circuit was bowed and all that stuff. I think we got some success in matching simulation with measurements, and I didn't show those here because I wanted to show the evolution. But it got a little closer, but it wasn't like substantially closer. So there's a lot more kind of discussions and decisions that we'd have to delve in on that. If he had more time, and you guys know this about all your research, there's always, Samir, you asked that great question about the switch. There's always so many things that you can ask if you had more time.
So yeah, we actually put the manufacturing deviations, right, for the PCB manufacturing. Their tolerances, they're usually the tolerances are pretty high. So that we kind of like a reverse engineered, like try to find out what could have caused the deviation between measurement and simulation. And then
So I also want to talk about why the bowing's there. And this is quite interesting, okay? Because I'm hoping that in your research groups, you guys are looking at things such as flexible circuits, additive manufacturing, because these are the materials and the technologies of the future, okay? I mean, that is, it's pretty obvious, okay? And we love to mess with new technologies. But the thickness of the MAM is the thickness of an eggshell. Okay, and so it is very difficult from a mechanical point of view to have something stay very flat that we model in HFSS to be very flat over a large range, especially when you're doing the material manufacturing, when it's that thin. Okay, so so there's a lot more that Prabhat could do on that.
Yeah, also the symmetry effects, like your top layer and the bottom layer, if it's not symmetric, what happens is, you know, you have different forces, right, on the top and the bottom.
That's
and then,
right.
So that causes them, yeah. And when we figured out later, you know, in our latest model of antenna, you know, and then so now the latest version is pretty flat, you know, after we evaluated. So
There is a question from Milad, I think. What is the boundary condition on the top of the simulation model? Did you consider the packaging effect?
So the boundary conditions are perfectly masked layer, which is just another word for radiation boundary. So it's perfectly masked. So any waves that hit the boundary are, you know, completely absorbed. Nothing is reflected, right? And then, so yeah, we didn't consider packaging. You know, we did consider the effect of like having metal objects nearby. You know, when there's something like a shielding enclosure, I think. So we used a shielding box, which is a perfect electric conductor around the antenna. So that was, you know, so that, and we saw some deviation in performance, like the S11 and S21 change, you know, because of that shielding structure. So yeah, and but yeah, PM radiation boundaries was something that we used, you know, for this simulation.
Great. I see Professor Treverio has a question.
Okay.
Oh, sorry. Did you want to add something, Kathleen?
No, go ahead.
Yeah, okay.
So thanks, very interesting talk. I have a question. How significant is do you think the interference of the antenna onto the traces and the power ground system could be something that needs to be modeled and eventually mitigated?
Actually, I want to make a comment on that, and then I want to talk about the S21. So generally, as long as there's separation between the frequency of, so on the cores, they're generally communicating at a much, I think, lower frequency than the 60 gigahertz, because you've got the clock frequency of your computer, and obviously there's, I mean, there might be some harmonics that you're going to have to watch on, but generally they could interfere. We didn't look at that part. It was something that was asked, but we didn't look at that part. But I do think that if the so I'm getting some good questions here, but if they're separated enough, then they could be isolated. I want to actually answer the next three questions here. So I don't know. I used to know what the typical losses are for routing in a PCB was. When I wrote the proposals, we had to do that. I don't know what they are offhand. So Prabhat, do you see Mr. Hassan M's question?
Yes, I do. So
and I don't have them off the top of my head. Do you?
Hassan's question was, yeah, you present S21 for chip using proposed method. What are the typical losses for routing through PCB? So it all depends on the substrate you're using, right? And the dielectric or the loss tangent, and you know, as well as the kind of transmission lines you have, right? So our first generation antenna was built using microstrip structures, so it was very open. It wasn't very shielded, right? So we had a lot of radiation loss, and then so we decided to go with the substrate integrated waveguide, which had like is a more shielded or enclosed structure. It's a closed structure, right? So
but what are they for existing? Like if you put, well, actually PCBs right now.
Few dBs.
A few dBs, yeah, because often they're FR4 that we use. Actually, so Colin, the plate, Prabhat, I think you did look briefly at a microstrip Yagi for briefly, right?
Yeah, we did look at, like, you know, it's different kinds of structures, you know, and then we figured, you know, we need something that's more closed structure, you know, like, so that's why we have those vias, right? So they help to kind of guide the waves, you know, in different directions, and you have less of the radiation loss, and then you also need to have a lower loss substrate to minimize the, and so that's why we can. So there's another question regarding the, you know, whether we could use a silicon-based waveguide, right? silicon is very lossy. I think the dielectric constant is very high. And so
No. Actually, the silicon-based waveguides, so you guys actually had, I think, no, she was at McGill. Sean, did you know Ramesh?
Yeah, she's in California now.
Yeah, but was she at Toronto? No, she got her PhD at Toronto.
PhD in Toronto, yeah.
Yeah, so you guys actually have an alumna who was phenomenal in the whole idea of silicon-based waveguides for interconnects. And she took a different career direction than academic. She graduated and she was at McGill. And so Ali, you've got some options that we did not look at, because that's not our area. You know, we're antenna people are going to look at the antenna solution. The other thing that I'm also seeing big time, and it's going to affect all of our lives, is the whole quantum, the quantum networking and the photonic stuff, because those are coming along. You know, the technology on those is coming along pretty quickly. So those are all we didn't look at this, but these are definitely technologies that you would and yeah, but the silicon-based waveguides provide the silicon is the waveguide walls, and the it's still air filled. So anyway.
Oh, if it's air filled, yeah, I think definitely.
Yeah. So silicon. Yeah,
Yep.
silicon integrated waveguides are like the it's kind of opposite, so that they're pretty interesting.
Yeah, I mean, they're like, let's say if you implemented this horn in a silicon structure, right, you'd be a lot more lossy, because it's, the dielectric constant is the loss is very high. Yeah.
But I'll leave that. But again, we wanted to get away from the wired part. But I mean, there's definitely some options here. So.
Mm-hmm.
Okay, well Dr. Hum.
Just a quick question. I know it's getting late, but yeah, I'd like to congratulate you both on some very interesting work. You've probably learned a huge amount here. I noticed you plot far field patterns, which, considering the interchip distance or inter-die distances are probably like they're not really in the far zone. So I'm wondering if you've thought about approaching it from more of an optimization perspective, now that you've tried different antennas, in terms of just trying to maximize that figure of merit that you pointed out earlier. And it's more of a near field coupling now that you're trying to achieve, right?
Mm-hmm. Yep.
And that's probably going to change I'm guessing, the direction that the antenna is going to look like, in terms of more like a surface wave launcher or some sort of near field coupling structure versus one that's optimized for delivery into the far field.
Well, I want to answer this first, Prabhat. Okay, so because this was always asked. Okay, now Prabhat, on your microstrip patch, when you use the far field requirement, are the antennas in the far field or the near field?
So because the microstrip patch was a lot smaller structure, right? So we're in the borderline,
Exactly.
In between.
What about the surface? What about the horn? They're
So
in the far field.
With the horns, we're in the near field.
You're in the near field.
Yeah.
Okay.
Yep.
Sean, so that's a great question. When we first started this work and we used single antennas that we were switching, and we were actually used PFAs that we changed. We changed their orientations. We were looking at single antennas, and
you invented the PFA, by the way. Anyway, go on.
I invented the understanding of the PFA. The PFA was invented in Japan.
Yes.
And I'll just tell you guys a funny story about that. Okay, so Dr. Hum and I both know a day, me more than he, when there was no internet and there was no wireless. Can you believe? Can you believe that? But anyway, at the time, and this is good about the PFA, NTT, which is Nippon Telephony and they were, so Japan was the leader of handy phones. So anyway, but I'll just tell you this is a good thing for the students. Whenever we found any papers that would discuss the PFA, this is in the early 90s, they were all written in Japanese. So you had to look at the figures to try to dissect what in the heck was going on. So anyway, so I didn't invent it, but the group that I was with handled it. Thank you for, yeah. So we were, okay, so the near field, far field. So, okay, so this is great question, Prabhat. When we were first looking at single antennas, we were absolutely in the far field, but, and this is a great question because I haven't thought about this. But as the antennas are becoming more sophisticated, i.e. the D, you know, it's 2D squared over lambda, as the Ds are getting larger, that they are getting in the near field. So you got a good, they're on that boundary. So thank you. Do you have any comments, Prabhat, on that?
So it's like, you know, we don't really need to look at the far field parameters, and, you know, but the thing is, the far field is related to the near field, right? So the coupling, and so that's something, you know, it's a factor, but it's not the factor now, you know, with the, you know, the far field being so, but near field is something that these antennas operate on. So you have other effects that are going on that needs to be you know, closely looked at. And I think the research going forward would be, you know, to design structures that are more for, like, you know, near field communication. So yeah,
I agree, because the 2D squared over lambda, that's really like a phase criteria for just
yep.
And it really has little to do with the actual amount of coupling. And what you're more curious about is the regime. You have more reactive field coupling where in the situation that you're in, or more radiative field coupling, right?
Yeah, I think we definitely have some reactive there. And then we did consider, you know, looking at like phase centers, like, you know, phase center, you know, is because we have a phase center would be a geometric different from a geometric center, right? And so that's something we could model, you know, but that's definitely something we want to, you know, in the future we want to look at. Yeah.
Okay, thank you.
Great. I think we should let you go. Thank you very much for the presentation and patiently asking our questions. This was definitely a very nice presentation and great work. So I'm going to stop.